can start.
Okay. Okay, I can share screen. Okay, so I'm going to cover basic molecular kinetics like you saw in Chem. Then we'll kind of build off that, go into Arrhenius, and then kind of even further go into like the stochastic kinetics that Professor Groves covered. Okay, so kind of pop quiz. Which graph corresponds to which order? You can either respond or I'll just say it in like 10 seconds. Okay, so the one on the left is second order. You can see that it has a very sharp decline at the start. The middle one is a first order. You can see that kind of looks like a decaying exponential. And the one on the right is a zeroth order, which has, since the rate of the reaction is independent of the concentration of the reactants, it's linear with respect to concentration. And here's kind of an overview. I'm not going to spend too much time on this, but just for your reference. So then kind of moving on. So one thing that kind of got hammered into your memory in Gen Chem is you can't state the overall rate law for a reaction just by looking at the overall reaction. You have to know the mechanism and find out the slowest or rate limiting step. But if we just go by individual steps, you can just simply write it as the rate being some rate constant K times the product of all the, okay, maybe I shouldn't use the word product, all the concentrations to their stoichiometric coefficient multiplied together for the reactants. So what are the units of K? So this depends on what type of order it is. So we can kind of actually just figure this out via algebra. So reaction rate is a change in concentration. So it should be molarity over time. And the units of the concentrations is molarity, of course. So you can set these two sides equal, and both sides have to have the same units because you can't compare apples to oranges. So we have on the left molarity per second, and on the right we have the units of K times M to A plus B plus C, which we can call the order of the reaction. So you can just divide by M to the order, and you get that the units of K are M to the 1 minus the order of the reaction divided by seconds. So this is something that could be like a multiple choice question on an exam. So it's just something to have in the back of your mind. So now from the rate law, moving on to the integrated rate law. So whereas the rate law told you how fast things are going, integrated rate law can tell you how much there is after a given amount of time. So this is for just a simple first order reaction that's irreversible. And you see that it's this decaying exponential. And then on the other hand, you see B kind of goes up in like a mirror image, basically. So kind of another thing that was on that table is the half-life, which is the time it requires for the concentration to reach half of what it was at the start of whatever period you're counting. So you can get this by just solving the integrated rate law and putting A of T equal to 1/2 of the initial concentration of A. So kind of the important thing for first order is that the half-life is independent of the concentration, which is not true for the second or zeroth. And that half-life is the natural log of 2 divided by K, which you'll find if you solve for the equation like on the first bullet point. And you can actually kind of estimate this on a graph. Like if you look at the one below, the max of the A concentration is about 4 blocks high. So you find what the X value is, where the Y value is 2 blocks high, basically. And that's about 1 3/4 blocks away, and so that would be your half-life. And then similarly, if you go to 3.5 blocks, which is 2 times 1 3/4, you get that it's 1/4 of the value, or 1/2 of what it was after the first half-life. So reversible reactions. So this is something that is very important. You usually see it with a different type of arrow, but I'm limited on what symbols I can use. So there's the forward reaction with a rate constant K of F, and then similarly, a reaction that goes from the products to the reactants with a rate constant K of R. So kind of the difference between this is you don't end up using up all of your reactants at the very end when it stops changing, and you end up with something called a dynamic equilibrium, which we'll often just call an equilibrium. So the key thing is that there's no net change at dynamic equilibrium. You still have forward reactions and backwards reactions happening, but they're just happening at the exact same rate so that you don't really observe a macroscopic change in the concentrations. So kind of comparing these two graphs, these are both first order ones, and you can see on the right that the asymptotes aren't 1 and 0. They're about 0.45 and 0.55. So you can, as you've seen in general chem, you have something that you can define as your equilibrium constant, which you can derive by setting the forward and the reverse rates equal to each other, and then just solving for something that's the ratio of the products to the reactants. Okay, so steady state versus equilibrium. So steady state is kind of a broader category. With equilibrium, there's no driving force. There's no free energy consumption that's required to keep it in this state. And all the concentrations don't change over time. Again, this is a dynamic equilibrium, so there are still reactions, just not a net change. So for steady state, you can say that something is in a steady state if the concentration of some, but not necessarily all, are constant. So often this could be like an intermediate of some reaction chain, but this often requires a continual consumption of some type of fuel to keep it going, unlike in equilibrium, which doesn't require anything to stay in that state. So if you have a reaction chain that goes A to B to C, and we'll say these are irreversible, you could have B, the intermediate, be constant. But the thing is, you're losing B because that can turn into C. So in order for B, the concentration of B to be constant, you have to have A and keep adding it in order for that to turn into B to offset it. So kind of where you'll see this a lot of the time is in maintaining concentration gradients, because you'll have something like sodium potassium where you have like ATP, and it helps keep the concentration gradients across the membrane. So one thing that I'll kind of go over, a difficult exam question from my year. So we have kind of this large series of reactions for the production of ammonia, and all these reactions are reversible. It's just not written very well, but just keep that in mind. So visualizing it. So if you've taken like Calc 3 or something, you might think of it as like a divergence or a flux, but it's basically like a net flow. So one example that you may have seen in lecture is like a sink filled with water. The water level will change if there's kind of a difference in the in versus the out. So if the water that's being drained from the drain is greater than the amount that is going into the sink via the faucet in the same period of time, the water level will go down. However, if like your drain is stopped up and it doesn't drain very well, then you can easily have the opposite scenario where you can have a net rise in the water level by blasting the faucet and just not having it drain well. So that's kind of a simple analogy, but it doesn't deal with like what happens if you have multiple faucets going into the same sink, or what if you have multiple drains. So I'll kind of go to a different analogy that might help. So think of it as like a population of a country. So population can change by multiple things. You could have births, or you can also have people immigrate to your country, but the population can also decrease from deaths or emigration, which means people immigrating to another country from your country. So to talk about the change in population, you can say that your change in population is equal to the births plus the immigrations to your country minus the deaths minus the emigrations, which you could rewrite as saying like dp dt is equal to the sum of the rates that would increase it minus the sum of the rates that would decrease it. And we're getting kind of closer to where we want to be in order to answer the question, but we haven't talked about stoichiometry, because you can't say like one person is born and that increases your population by 2 or something like that. So first, to solve the question, we should identify all the reaction steps where our species of interest appears, which is H adsorbed. So you can see on the right in the red boxes, it's in step 4 and 5. So we kind of just only focus on that. And then you should also keep in mind the reverse reactions, because we'll be using those as well. So we end up getting 4 kind of one-way reactions that we care about. The forward reaction for 4 and the backwards reaction of 5. Those both produce H adsorbed. And then for ones that use it up, that would be the reverse of 4 and the forward reaction of 5. So so kind of as I showed in the population example, you have like a bunch of sums, 2 sums that you kind of take the difference of. So you basically treat each one-step, one-way reaction, treat each one as a one-step reaction, and then you multiply it by the stoichiometric coefficient of your species of interest, which would be the stoichiometric coefficient of your H adsorbed. So, and you kind of write the rate laws you've seen in general chemistry. So like for the forward reaction of 4, where it's H2 adsorbed goes to 2H adsorbed, you would write that as 2 for the stoichiometric coefficient of H adsorbed times K4, which is the rate constant for that reaction, times H2 adsorbed concentration. And it's to the first power because that's the stoichiometric coefficient for H2 adsorbed. And you can do some analogous thing for all the other ones. And so for your final answer, you can write as dH adsorbed dt equals the sum of all the coefficients times the rates minus that produce H minus the sum of the coefficients of H times the rate of the equations that use up H. So that ends up being this kind of long expression. But this gives you kind of a very generalized equation that you can apply to anything. Okay, and that's all I have to say. So I'll stop sharing. If you have any questions, you can ask in the chat.
All right, so hey everyone. So jumping off what John just talked about, we are going to talk about what factors can influence reaction rate, specifically those factors in the context of the Arrhenius equation. So of course, when we talk about what can affect reaction rate in our biological perspective, we think of enzymes and catalysts. And I think it's when we start talking about reaction rates and catalysts and intermediates become a little more abstract, and it's easy to get confused between the two. So I wanted to go over that quickly. terms of these equations. So catalysts, they don't appear in the net reaction, right? Normally we just write them above the arrow up here, but they will first appear if we break this net equation into its separate half reactions. We can see that catalysts will first appear in the reactants, reappear in the products. Intermediates also won't appear in the net reaction, and they'll do the opposite of catalysts. First appear in the products, then the reactants. So if we can just walk through this real quick. D is going to be our catalyst. First appears in the reactants. That combines probably to form some, if it's a biological system, enzyme substrate complex. E, and then that will react with our other molecule, B, to make C. E gets used up, so our intermediate E goes away. We form our product C and reform our catalyst D. So this is pretty straightforward. It can get easy to mix up, especially when we talk about things in terms of A, B's, C's, and D's. So just keep track of everything. Now we'll talk about what makes a reaction happen, and that is molecules need to collide. Talk about that in terms of collision theory. And we usually imagine, some system, we got two different types of molecules bouncing around in there. And of course, it makes sense. You need molecules to come into physical contact with each other to then react to form a different product. And from that, it makes sense that the more often you have these collisions, the more often you'll have a reaction and therefore a higher reaction rate. You can think of some of the factors that may affect the number of collisions in a system. You could increase the temperature, give the molecules more kinetic energy. You could also, like in this example, increase the number of molecules, the concentration. Those will all work to increase the number of collisions and therefore the reaction rate. And it's all really a probability thing, right? Is how often am I going to get these molecules to collide and react? But we also have to look at productive collisions, meaning every time a molecule reacts doesn't mean you're going to have an actual reaction. There are two main factors that influence that. First one we'll talk about is orientation. You need your molecules to collide in the proper orientation because you need the bonds between the atoms of those molecules to form in a specific way. So let's take this example. We have NO plus O2 going to NO2. And these are the Lewis structures down below. As you can see, we have our two oxygens attached to our middle nitrogen and NO2. And how this works, if you treat these molecules as hard spheres and the bonds as like sticks connecting them, is we need one of these oxygens on O2 to hit this NO on its nitrogen side. That way we'll have this bond form such that we have nitrogen in the middle, our oxygens on the outside. We can't have this O2 collide with the NO oxygen, right? Because then we'd have the bonds in a completely different order. And that would be a completely different molecule. Probably wouldn't form anyways. So orientation is going to be important. And we'll talk a little bit more how that can relate to catalysts. But the other thing, the other thing that will affect collisions is, of course, the energy they have. This is probably the one we're most familiar with, which is activation energy. When our molecules collide, whatever kinetic energy they were moving around with, and what they collide with will get converted to potential energy, and that can help form or break bonds. It'll eventually do the reaction. And you need enough energy to react, which is on this reaction coordinate diagram denoted by E sub A, your activation energy. We have going from the reactants an energy barrier, and at the peak of that is your transition state, which is the highest point of energy. And we can easily measure, for the forward reaction, the activation energy just going from the reactants up to the transition state. And if we treat this as an equilibrium reaction, we can also, from the same diagram, get the reverse reactions activation energy. It'll be this forward activation energy plus this arrow here going from the products up to reactants. But let's talk a little bit more about how reaction energy relates to our term RT. And if we define temperature at 300 degrees Kelvin, we have our RT term equal to about 2.5 kilojoules per mole. And that's, we've talked about in class, is thermal energy, right? Just at that temperature, the energy the molecules have moving around in their system. And how that relates to activation energy is if you have this activation barrier and the energy gap here is much higher than 2.5 kilojoules per mole, if you just observe the system at 300 degrees Kelvin in its container, you'll find that most of the molecules won't react, right? Because that 2.5 kilojoules per mole energy is not enough to get over that hump. And the converse is true. If you have the activation energy less than RT, you'll find that most of the molecules in the system will react and you won't need to add anything to it. So that's just an interesting relationship to keep in mind. And that overall gets us to our Arrhenius equation given to us by K is equal to A times E to the negative activation energy over our RT term. And in this equation, we have all those factors that we talked about in collision theory. We have our activation energy, our thermal energy, and with an A, which is called our pre-exponential factor, that includes the frequency of collisions and also the geometry and orientation of the molecules. Normally, we'll determine A experimentally. Another thing though is that we can convert it to this form, which will give us a more linear form to deal with and is a little easier to do calculations with, as we'll do with an example problem, but find a temperature dependence there. And another thing is you want to keep track of your units, like with the first, second, third order reactions. Your units of K will change, so will your units of the pre-exponential factor. So just know what order reaction you're dealing with, and that will determine what units you have. So before we do example problem, we're going to talk about what can change our pre-exponential factor. So of course, we already talked about the frequency of collisions, right? That can be related to concentration and also temperature, which I forgot to put on there. But increasing the number of collisions that'll happen will increase the reaction rate. Therefore, that will increase our value of the pre-exponential constant. These reactions, we can also compare different reactions and compare their pre-exponential constants, assuming all other factors are constant, like frequency of collisions. And you can see, we went over this example right before, 2NO plus O2 going to 2NO2. Compare that to this left reaction where you have two oxygen radicals combining to form O2. So again, treat them as hard spheres, and you can see that these two oxygen radicals, they can, if they're bouncing around in a container, they can hit each other from any angle, right? And in theory, you should still form O2. So there's more ways, basically, these molecules can collide such that they're in the right orientation to react. There are less ways to do so with NO and O2. And you can imagine the more complex molecules you're dealing with, or even the more molecules within an equation, overall, the less possibilities of orientation you have for productive collisions. And the more limited you are in what orientations you need, the lower your reaction rate, the lower your K value. And finally, tying this all back into catalysts. Catalysts, of course, will decrease activation energy, but they can either decrease activation energy, increase your pre-exponential factor, or do both. And they do that by increasing the rate of your productive collisions. You can think about in biology, catalysts are enzymes, right? And enzymes have an active site. That active site orients molecules in such that they can more easily react. And in transition state theory, basically the active site more or less approximates the orientations of the molecules at their transition state. So it helps the molecules, the substrates, when it comes in, get oriented such that it's at the highest energy it can be, and then that'll push the reaction forward, decreasing the activation energy. But one thing to know is that the catalyst, because it is an actual molecule or enzyme, it can actually change the mechanism you're dealing with. So your kinetic measurements in these kinetic theories may get slightly messed up from that. But I think that's a little beyond the scope of this course. But just keep that in mind. Anyways, are there any questions about what I just discussed? Okay, we'll do a quick example problem. So you have, this is somewhat similar, well, pretty similar, pretty similar to your homework problem. So you have a graph showing, this is for the catalyzed reaction. These points are 1/600, -1.5, and 1/100, -3.5. It's asking you to find the activation energy x-axis in terms of 1 over T, units 1 over Kelvin, and your y-axis is ln of K. And second question, once you have the activation energy, can you predict what will happen to the uncatalyzed reaction at if your temperature is 300 Kelvin and RT is equal to 2.5 kilojoules per mole? Will that uncatalyzed reaction happen at all? So just take a minute, I suppose, just think it through, and then we'll go through the answer. And if you have any questions, just unmute yourself and let me know. All right, we'll just go through it now. So for the first problem, you can use your rearrangement of your Arrhenius equation, ln k is equal to this. So our x variable in this case would be 1 over t, y ln k. So our slope of this line is negative e sub a over r, right? So we can use that to then just find the slope. I get negative 240 is equal to that value, and then just multiply by r and that negative 1, and we'll get our activation energy is 1.995 kilojoules per mole. And then for the second part of the question, asking, all right, this was for the catalyzed reaction. Do you think the uncatalyzed reaction will have any chance of happening at RT equals 2.5 kilojoules per mole? And because the catalyzed reaction activation energy is so much lower than the value of RT, we can also say with pretty good certainty that the uncatalyzed reaction won't happen significantly. So yeah, that's all I have for now. Are there any questions? All right, well, then I'll stop my share. Feel free to message me in the chat and hand off to the last tutor.
Okay. All right, so hi everyone. So for the last topic for today, I'm going to go over mRNA transcription kinetics and also talk about the Poisson distribution. So this should be kind of a rehash of the lecture you had on Wednesday with a little bit more commentary on what exactly the Poisson distribution is. So that said, first, let's go to the relationship, the kinetic relationship that you derived in class, specifically on mRNA copy number. And so this is straight from your lecture slides, but this is the kinetic scheme that we were working with when we were talking about both mRNA transcription and also translation. For the slides today, I'm just going to focus on transcription because I think if the math makes sense for transcription, you can see the slides and it's kind of very similar for protein translation. But essentially what's going on here is that you're starting off with DNA, and we make the assumption that we only have one DNA molecule, meaning like only one allele or one copy of the gene. And there is some rate, Kr, that represents the transcription rate at which new mRNAs are being made. And there's also a degradation rate, K negative R, that's proportional to the amount of mRNA you have. And of course, the number of mRNA or the copy number of mRNA at any given point is represented by NR. And so using using this setup, we derived a relationship in which we made, essentially, we came up with this expression. And the way that we came up with this is that we kind of looked at the forward rate of mRNA being transcribed, and that's related to the amount of DNA you have. Here it's written as ND, but we later assume that's just equal to 1. And then also you consider the rate at which mRNA is being degraded or decreased, and that's proportional to the amount of current mRNA molecules. And then we make one more assumption in order to derive this steady state conditions, which is that we assume that the entire reaction is at steady state. And as John pointed out there is a subtle difference between being at steady state versus being at equilibrium, because all that's required to be at steady state is that the overall concentration, or the overall, in this case, number of mRNA is not changing. So because we're using the steady state assumption, we can assume that dNR over dt is equal to 0. And that's what allows us to come up with this expression. And then we also denote the concentrations of both the DNA as well as the mRNA copy number at steady state by this subscript SS. And we eventually come up with this relationship. So by looking at this kinetic scheme, basically what we're saying is that if you have some type of biological process like this, in which the mRNA is being transcribed at a rate Kr, and it's being degraded at a rate K negative R, and if we ignore protein translation for a minute, then we can approximate that if you just let the reaction go and let it find a steady state where it's not exactly at equilibrium, but the concentrations are kind of just changing or just staying the same, then we would expect the mRNA copy number to be somewhere around this. So we would expect that the total number of mRNA molecules should be very close to this NR at steady state. And then, as Professor Groves showed you in the slide, this is not exactly a good model for what exactly is happening. In the case of mRNA copy number, you might have a decent description of what's going on, but when you look at protein copy number, and this should say protein copy number instead of mRNA, we see that just using one number or just using the average to describe what's going on with the total amount of protein you have at any given time is not really a good model or a good representation of what's really going on biologically. And so for today, I'm just gonna focus on what's happening at the mRNA level. But what you can already see here is that this NR of SS, as was mentioned in lecture, this just represents the average of all of these fluctuations. So if you took the number of mRNAs at any given point and you average them all together, you'd end up with this relationship. But what you can see is that there's a little bit of fluctuation that's happening at every given point. And although this looks Gaussian, we'll find out that this is actually not represented by a Gaussian distribution, but it's by a different probability distribution. And so based on this, we next move on to what Professor Groves refers to as stochastic kinetics. And basically the idea here is that we're combining probability with kinetics. So again, this is the same kinetic scheme that I showed you in the second slide, in which you just have mRNA being transcribed and also degraded, and we're just ignoring protein translation for the moment. And so with this in mind, we can actually model this as a sort of chain of events or a chain of probabilities in which there's a certain probability of transitioning from one state or another. And one representation of this would look something like this. And so let me just explain what this diagram means. So each of these circles, you can think of them as representing states. So this circle NR represents a state in which you have NR as your number of, that's your mRNA copy number. And this is the state where the mRNA copy number is equal to NR minus 1. And so in theory, this could go from 0 all the way to infinity, but because at the end of the day, we're making this a probability distribution, realistically, as you get to larger and larger numbers, the probabilities of those happening are going to be basically 0. But just for this example, I'm only looking at these 3 states. And so when you're in a state like NR, you have some probability of transitioning to other states that's happening at some rate. So in this case, the way that you go from NR mRNAs to now having NR plus 1 is you need to have a new mRNA molecule be transcribed from the DNA. And we know that that happens at rate Kr. And so all the transitions to the state where you have one more mRNA is just by Kr. And then consequently, you can also go backwards in the sense that you could lose one mRNA molecule. And we know that this is based on the rate of degradation, which is K negative R. And importantly, this is related to the total amount of mRNA you have. It's proportional to the current mRNA concentration. So this is our model for what's going on. Professor Groves also expressed it this way. Just personally, I find this a little bit easier to parse, but these are essentially 2 equivalent things. And all we're trying to represent here is that instead of using only kinetics, we can bring in probability to think about the entire system of mRNA copy number as being distributed into states, where each state represents a certain number of copies of mRNA. And then we can use our kinetic relationships to represent this in terms of the probability of transitioning from one state to another to eventually come up with a full distribution in terms of what is the probability of having this much mRNA at a given time. And so now let's actually compute that probability distribution. And so we make, again, another assumption about steady state, which is that the net flow into or out of each state is 0. And so another way that you can think about steady state is that because the inputs are equal to the outputs, you can think of them as pretty much offsetting each other or canceling each other, so that essentially the flow is equal to 0, or its net flow is equal to 0. And so again, this is from your lecture slides, but because we know that the net flow is equal to 0, then that means if we let the process of mRNA transcription and degradation just happen by itself, then eventually it will arrive at some steady state where the numbers of mRNA usually aren't changing too much, but specifically in our case, the probabilities of being in each state aren't fluctuating by a whole lot. And so that's why we come up with this relationship here, that the change in the probability of having this number of mRNA is equal to 0. Like, it doesn't change with time because we're at steady state. And so then we again use the rate of mRNA being degraded as equal to the rate at which mRNA is being added, and we come up with this relationship here. And you can refer to the slides to see all the additional steps that were done after this point. But the key thing here is that after you come up with this, and you combine this with the fact that all of your probabilities at the end of the day have to add up to 1, because the probability of having 0 mRNAs plus the probability of having 1 all the way up to having NR mRNAs, because it's a probability distribution, all these probabilities at the end of the day have to sum up to 1, we come up with this equation. And here, what we're saying is that the probability of having this amount of mRNA is given by this expression. And the reason why this is pretty meaningful is that this is the equation for the Poisson distribution, which I'm going to now talk about in a bit more detail and help maybe add a little bit of commentary on how to interpret this. So before we get to the Poisson distribution, I just want to mention probability distributions very briefly. So you've probably seen a lot of probability distributions before, and you've probably heard me throw around the term a lot. So let me just provide like a very simple working definition, which is that a probability distribution is essentially a function that just assigns a probability that a certain event will happen. So one thing that we can ask is, let's say we toss 100 coins that have a 50-50 chance of being heads or tails. If we want to know what is the probability that 62 of them will end up as heads, we can model this with a binomial distribution. And here are some probability distributions that you've probably seen in the course already. So this over here is the normal distribution, also called Gaussian distribution. And these different ones are just plotted based on having different means and having different standard deviations. So this is the equation that essentially relates the probability of seeing some x. And you don't really need to know that this is the this is known as the probability mass function. You don't need to know that, but this is just there in case you wanted to know. Another thing that you should know about probability distributions is that when we're talking about them, there are two important parameters that we like to talk about. So one is the mean of the distribution, essentially like where is it centered, and also the standard deviation, which is a measure of how spread out the distribution is. And so here we have the binomial distribution. And the binomial distribution, what it's modeling is, let's say you have n trials. So in this case, you have all of these binomial distributions have n equal to 300, meaning you have 300 trials. So 300 coin tosses. And then each of these parameters, either 0.2, 0.5, or 0.7, represent the probability of success. So in our coin toss example, the probability of success is the probability of having heads, which is 50% or 0.5. And so in that case, the coin toss example corresponds to something like this. And as you would expect, if you toss 300 coins, you'll probably expect a result in which about 150 are heads, about 150 are tails. And then the farther you get away from 150, the less and less likely it becomes. And here is the formula that basically just represents the probability of a certain outcome happening. So here for n, you would just plug in the number of coins that you're tossing, which is the number of trials. And then x is the number of, or is the outcome you're looking for. So in the case where we're asking what is the probability of tossing 100 coins and getting 62 heads, we would plug in 100 for n, 62 for x, and then our p and q are both 1/2. And then another thing that you should just know about the binomial distribution is that the mean and the standard deviation are given by these two. So those are just some probability distributions that you've already seen. And so now we can talk about the Poisson distribution. And so this is what the Poisson distribution looks like. And here I've plotted, and here these are plotted with different values of lambda. And as you can see, this is the formula that relates basically lambda and the probability of observing something. So if you have a Poisson distribution in which lambda equals 4, and you want to know what the probability of seeing x equals 3 is, for example, you plug in 3 for x, 4 for lambda, and it would roughly correspond to this point, something like that. And then the interesting thing about the Poisson distribution is that you really only need one parameter to represent both the mean and the standard deviation, because the mean is lambda, standard deviation is square root of lambda. And so here comes the interesting part about interpreting the Poisson distribution. So I was told this anecdote, so I'm just going to pass it on to you. But I mean, the Poisson distribution was named after the mathematician who came up with it, but I've been told that Poisson in French means fish. And the Poisson distribution is often modeled as a good way of representing the waiting time for an event to happen. And the Poisson distribution can actually be derived by looking at the binomial distribution. But the way that we come up with a Poisson distribution is, let's say we take lots and lots of trials. So instead of tossing 100 coins, let's toss 1,000,000 coins, for example. But also the probability of success becomes smaller and smaller. And this is why the Poisson distribution is kind of modeled for things such as fishing, because if you've gone fishing, you know that you have to wait a really long time before you catch any fish. So a good way to model the probability of catching a fish is you can think of the Poisson distribution as basically saying, let's say there's some probability that you will catch a fish in the next minute. What is the probability that if you're waiting for 60 minutes, you will catch some number of fish? And that's how the Poisson distribution kind of models arrivals or rates. And specifically, this parameter lambda is really important when we're thinking about the rate or the number of arrivals in a Poisson distribution, because this lambda is called the rate parameter, and it's used for modeling the number of events per given time. So in the fish example, if you're going fishing and you're catching 3 fish per hour, you can use that as your value for lambda is equal to 3, and then you can ask questions like, what is the probability that you will catch 1 fish in the next hour or 4 fish in the next hour? And then you can also chunk it up to be in increments of 30 minutes, and I'll go over some practice problems like that. So once again, this is what we derived for the probability distribution of mRNA copy number. So a question that I have for all of you is, based on this Poisson distribution that we derived, and this as like the generic form of the Poisson distribution, what is the rate parameter in our example? And so feel free to just type 1, 2, or 3 in the chat based on what you think it is. And I'll just give everyone a few seconds to think about that. Okay, so I guess I'll just go ahead and go over the answer. So in this case, the rate parameter for this Poisson distribution is kr over k negative r. And the way that you can see this is that if you look at the formula for a Poisson distribution, the rate parameter is always raised. So you always have e to the negative lambda. And here you have e to the negative kr over k negative r. And then in the Poisson distribution, you also have the rate parameter raised to the power of x. And in this case, we're considering nr. And here you have kr over k negative r raised to the power of nr. So the rate parameter for this mRNA copy number example is given by this. And so next, I just want to go over a few practice problems so that you get a little bit of intuition on how to use the Poisson distribution in general. So first, let's suppose that you're, I guess, on the sidewalk or something, and you're just counting the number of buses that are passing you every hour. So if you count that 4 buses are arriving, what is the probability that in the next hour you'll only count 2 buses? And so we can model this problem as Poisson distribution, or these arrivals is happening as Poisson arrivals. And in this case, lambda is 4 because you're counting 4 buses per hour. That's your rate parameter. And then we're essentially interested in asking, what is the probability of observing exactly 2 buses? And so that's finding probability that x equals 2. And once again, this is our PMF for Poisson distribution. and we just plug in lambda as 4, when we plug in x as 2, and we end up with this probability that about 14.65% is the probability that you will find only 2 buses if normally you see 4 and you're waiting there for an hour. And so we can also consider another example. So suppose there are 300 molecules of a protein that are being newly formed every single hour. We can also ask, what is the probability that we will see 10 new protein molecules that are translated from mRNA in the next minute? And so here, this problem is a little bit different from what we just went over in this case, because here, our rate parameter was 4 buses per hour, and we are asking how many buses will we see in the next hour. But in this case, we're saying that we see 300 new molecules every hour, but we're only interested in how many arrivals you see in the next minute. And so what we need to do is rescale this parameter so that instead of being per hour, it's per minute. And then if you rescale it, you'll get that lambda is 5. So your rate parameter is that you're expecting to see about 5 newly formed protein molecules every single minute. And then that just means that lambda equals 5. And we're asking, what is the probability of observing 10? So we're interested in probability that x is equal to 10, given that lambda is 5. And you can compute the math yourself. But also, it comes out to about roughly 1.8%. And so just a disclaimer that I want to make here is that in both of these two examples, we're assuming that the problem that we are given can be modeled as a Poisson process. And so normally this is not necessarily true. You either need to be told in the problem that it's safe to make this assumption, or in the case of the mRNA copy numbers, when we actually derived the probability distribution, we saw that the probability of observing this many mRNAs is given exactly by the Poisson distribution. So we know that it's necessarily true to apply that assumption. So that's all I have for today. I guess we still have a minute left. So does anyone have any questions? Okay, so I'll just stop screen sharing and I'll stop the recording.